That looks good. Okay. So this talk is also a little about systems, because systems are important, but I have phrased it in the. So what happened now? Let's see if we can do this one. Okay, I know it because I put in my box there. Is this actually the case? And the reason why I want to ask this question is, of course, that so far life has only been found on Earth, and this means, of course, that life on Earth is controlling and directing all the thoughts we have about life elsewhere. And as astrobiologists are generally in good positions and well fed and so on, Earth seems to be an ideal place to have life, at least our kind of life. So I want to investigate a little how this reflects further on onto the subjects. One of the interesting things is, of course, that the only evidence we have about life is from Earth, and based on this evidence we can reach slightly dissimilar conclusions. Like life will be found everywhere unless we do something very careful to prevent it from coming. Life is a disease that attacks any healthy planet or moon. And the other conclusion, life is probably only found on Earth. And because we are so nice and so beautiful, we must be created by God, to put it down to the basic arguments. And you have probably, all of you, read some of books that represents one or more of these, where Earth comes into mind as one. But let's try to explore a little the argumentation in this. The point is, of course, that the evidence we have is interpreted according to the bias we have. And this being, what should we say, not unified science, but perhaps diversified science, which means that I, as a physicist, I know a lot about the solar system, but when I want to find out how life existed on Earth back then, I start reading some books, and I say, here's a point that I can use, that supports the viewpoint I'm reading this book with. And of course the biologist will go the other way around and say, this is an interesting fact about solar system formation, because that exactly presents important information on how life was created as I want it. So it's this kind of behind the scenes activity. So the point is, of course, that we are sitting after having adjusted to the Earth for 4.5 billion years. And perhaps more importantly, we are also sitting here after having adjusted the Earth for 4.5 billion years to fit us. And has this been an optimal process, or could it have been done much easier if we had had a better place to be? How quick could life have developed? If now we had optimal conditions, could we shorten down the periods that it takes to create us, the natural endpoint of life, to a much shorter time, because in that case some hotter, warmer stars becomes much more interesting for exobiology. Because main argument for looking at solar-like stars is that we need a long time to create life. So, well, this is impact versus time before presence in billions of years, and one of the basic things that have come out of the space exploration of the solar system is, of course, that we have been able to catch some rocks from the moon and to sort of establish an absolute time scale that we can use to correspond to the relative time scale we can produce by looking at quasar intensities and so on. So this is what we would call the Rosetta Stone of the solar system. I'm sad to say when I lecture on this, it doesn't help to tell the young students that this is the Rosetta Stone, because they don't know what the Rosetta Stone is. But anyway, we are talking about life starting in this period, around here. Let's look a little at this point here. There are several schools in the formation of the solar system. One of them will say that this is the tail of the accretion process that gathers together all the stuff that forms the planets, from smaller planetesimal and so on. And the other one will say that what we are seeing is actually only a tail of a late intensified bombardment. Some people have reanalyzed the stones brought back from Apollo, and now they seem to think that a lot of the basin-forming impacts all occurred around this time. So we have here a cataclysmic epoch in the formation of the solar system. And now it of course becomes important, what is the shape behind this thing? Because if we look at it, we say we have the earliest isotopic evidence of life right here at the end, which of course have made this tremendous change in the ideas about life, from being something that was so extremely difficult to make, that corresponded, as I think Hoyle put it, that a thunderstorm passed through a junkyard in Los Angeles, and when it has gone through, there was a 747 standing ready to take off. So that was the previous idea about how difficult it is to produce life. And this very early evidence of life have changed the opinion to that life comes very easily, very quickly. As soon as the right chemistry is available, then we will get life. Very, very quickly. But if we look at it, the formation of the Earth and the Moon from simulations by a lot of different people ends up with times around 10 to 100 million years. And then there is a cleanup phase. I mean, we first use up all the major material, and then we have left the debris, and then we do a spring cleaning and remove all the junk from the inner solar system by putting it under the carpet. And at the same time, we also have the delivery of the water. And there is also some interesting thoughts on this now, that it seems that the water content on the Earth, to a large extent, is coming from the snow line or ice line or whatever you call it, the region just inside Jupiter. So it's just from perturbations you will get a lot of ice into the inner solar system, which also means that it would be a natural thing when we are forming exoplanets to find water on planets within the habitable zone.
Also without Jupiter?
So far they only found the Jupiter, so that's the most question at the moment. But 10 to 100 million years, that means that basically the end of the inner solar system was formed around here. So did the cleaning phase really look like this, or did it have a much sharper drop and then a flat plateau, giving us suddenly, before the cataclysmic event, several hundred million years where we had water and where we could make the chemistry that is needed to produce life. So life might not come as quickly as we have thought. Especially now when we have realized that life can go deep and survive around the mid-ocean vents. It can even go down into the crust and survive without water if necessary. And I'm not sufficiently well versed in biology to tell whether the egg or the hen came first. Whether we started life in the shallow waters or whether we started deep in the middle, and I think that there's a lot of work to be done before people really get the timing out on the early life. But there is at least a possibility there that life could come at a much more leisurely pace.
What is this cataclysmic bombardment? Essentially, it's a cometary bombardment?
It's a bombardment. It's a bombardment. It could be, for instance, an obvious scenario could be that we had not the usual 4 inner planets. We might have had 5 or 6, and 2 of them collided, which would suddenly give you a surge of debris in the inner solar system that again had to be removed. It could also be a severe perturbation in the Kuiper belt as Neptune is moving out in this period, that suddenly would give you a flurry of comets. It could be a passing star generating perturbations in the outer Oort cloud and so on. So there are lots of possibilities that could be seen as a cause of this. Yes?
How about in the planet formation schedule? When did the tectonics start?
The what?
Tectonics, yeah. How
The
fast do you
tectonics.
get the crust? I mean, you need some sort of crust. Is that a 10,000 year or 100,000 year or 100,000 year? So when would you get the hydrothermal vents, for instance?
If you start having oceans,
Right. When is that? On this graph?
the water comes in this period.
But would you have the tectonics also already?
That's a good question. I don't know.
I have also some comments. Maybe we do that at the end so we can talk here.
I mean, I'm just opening some possibilities in order to get a discussion going about this. So there are various possibilities here.
But how that water came from them? You're saying that water came from what is the process of transfer from the...
I mean, you have a lot of planetesimals. The planetesimals are perturbed by Jupiter.
Okay.
They are interacting with one another. You have near encounters that will suddenly flip their orbits, and they will move up and down in the distance from the sun. You have eccentric orbits and so on. So you get a lot of transfer of material in and out in the process of forming the solar system. So that's where at least some of the water is coming from. The old idea that it was coming from all comet clouds seems at the moment not to be doing too good, because the deuterium content in the comets we have studied is about 2 times too high. So the relationship between ordinary water and deteriorated water would be different in the oceans if it came from outside. So it's an acceptable theory that it came from fairly close by, and in this context Jupiter is fairly close by.
So the deuterium from outside is high relative to inside.
There's a gradient in the deuterium content.
But is there a deuterium measurement available for this region?
The what?
Is there a isotopic abundance measured for this region?
This is-
which water came?
This is measured from the comets that passed by. So this was this thing.
How much is this deuterium content of the comets changing? Because we still are speaking about 4 billion years.
They only have 3 measuring points. They measured 3 comets.
Yeah.
And they
Exactly, but
are
they are measured now.
exactly-
They are measured now,
Yeah,
not
but- yeah.
4 billion years
No, no,
ago.
No, but
They were here probably.
then you come up with a deteriorating theory. Something that will evolve the comet and give more and more deuterium. Until we have one of these, then we assume that in that respect, at least it basically reflects the original content.
But there should be some theoretical estimates directly on this production rate, I guess.
Yeah, but D over H is produced by supernova also, or what? Can somebody tell us what is the physics which generates D relative to H? I mean, what fixes the value?
D is Big Bang, right?
Yeah.
And why is
That's
it
Big
then?
Bang that fixes the value.
But if that's the case, why is then the inner part of the Earth having less DH?
No, in the inner part of the solar system.
In the part of the solar
Yeah,
system.
right. And why is that?
I mean,
But then we are already in trouble.
oh yes, we have.
Yeah.
No, but I thought that the inner part of the solar system having the
It's the second
had
thing,
deuterium is
it's
due
the
to the
solar system, which is-
biological process.
Yeah.
Isn't it true?
Can you repeat again? So, I mean, you're saying it's biology which changes the
ocean
H?
water having the higher deuterium. So it's due to the biological process.
We keep that also for the discussion, so poetry, I think, is some discussion.
But the point is that, of course, we have had this idea that as long as we had the huge impacts, then nothing could survive. Now, of course, not all impacts completely evaporate the oceans. Even major ones will only remove, say, up to 100 meters. And if you have 3 kilometers of ocean, then the lower kilometer is not very disturbed. So that's one thing, and the other thing is, of course, that as time goes by, especially in the cleaning up process, we will get smaller and smaller projectiles. And even if we talk about sterilizing the Earth with huge impacts, what does that mean? Does that mean that we reduce all prebiotic material to atoms? Do we reduce it to smaller molecules? Do we hardly touch the molecules? Do we only reduce whatever they have made in order to start life? Or what do we actually mean when we say we sterilize the Earth? It's such a nice picture, but what is the content of it? And then, of course, if we go to panspermia, then timing sequence on Earth is not very relevant. So there are lots of possibilities of putting question marks about this. Also, the new idea about that life came so extremely quickly. However, life does change quickly. I mean, now I'm just from reading a flurry of biology books. It seems that nothing much happens until we get to the eukarya, until we get a nucleus, until we are able to make larger cells that can sort of eat the other cells. And There seems, however, to be some questions there. Some biologists say that this actually goes back to 3 billion years ago. I noticed yesterday in Science there was a report for a biology conference where people now are claiming that they are finding nuclei or pre-nuclei also in the prokaryotes. So what should a poor physicist get out of this? So I hope that somebody will give me some good hints on what to get out of this. But I mean, it seems to be a bad picture where we have uncertainties of 1 billion years in our backyard. So, but this happened, and I mean, I hope somebody in the discussion will come up with a reason why it happened when it happened. Because making a bigger cell with nuclei that's able to fight all the other cells and win seems to be a good idea no matter when. What are the processes that made it happen just then? And then again, nothing much happens until we get to the multicellular life, and then of course then we have the Cambrian explosion, and then everything gets into high gear, except for some periods where things doesn't move very quickly, but then we can sort of steer it up a little with an impact or two. It seems that life sort of comes in jumps, following changes in the surrounding conditions, and I have read various estimates how quick it could be. 400 million years comes to my mind, which would sort of make the Earth less than 10% efficient. And this is the ideal place for life. But one of the problems that I think need a little more thought is, of course, that the development of life stops when the top species in the feed chain sort of fills out its ecological niche nicely. And then it becomes vulnerable. And then we get an impact, and then we remove the top of the feed chain and we give possibilities to everything else. I mean, being a mammal 70 million years ago was not nice. Earth was not a good place to live. But then we had a nice impact, and there was room. I mean, it has to be said that this impact was only part of the cause. There was also a change in the oxygen levels, which meant that with the poor respiratory system that the dinosaurs had already, then the mammals was on the verge of taking over. They might even have done it without the KT event.
So you're predicting we will be destroyed tomorrow and the ants will take over?
No, now we are trying to prevent that. You know, that's why we have space watch and all this. That's why we have space flight. Follow up on Richard Dawkins' idea about the selfish gene. This is the selfish gene's way of avoiding being obliterated by an impact. We go out and select multiple planets to live on. So the time that has not been used on developing the life has been mainly used on changing the atmosphere. With the introduction of oxygen as the main thing, but actually there are oxygen in methane in low levels, basically because of loss of hydrogen, which leaves some free oxygen that can go into various processes, but has normally been kept down, the level of oxygen in the atmosphere, by being absorbed in the ground. there has been enough methane in the absence of oxygen to give us, together with the CO2, to give us a hothouse. And it is interesting also that as soon as we have just 1% of the present level of oxygen, which we had around the 2.52 billion years ago, then there will be generated enough ozone to protect us against the UV. So that there might be one explanation there for when larger cells more exposed to UV could start forming. But this is guesswork. And one of the interesting things is that this change, the periods, also occurs when we have a snowball Earth episode, because the starting oxygen removes the methane hothouse and creates a snowball, because we also get more water vapor in the air, and that is not stabilizing or the forcing effect. It's an anti-hothouse effect. So that will, when freezing starts, really move it along. So we have snowball Earth, and as we all know, we also had snowball Earth just before we started making the Cambrian explosion. So it seems like there is an effect here, what we could call an ecological sweep, where we, by freezing everything down, removes perhaps the dominant things and makes all kinds of possibilities open. Afterwards, when we start with having the high CO2 content to remove the snowball, which then will, of course, further a lot of plant life, and then we get a lot of oxygen, and we will have a lot of animal life coming up top of that. So one of the interesting things, one of the arguments that I will pursue a little, is this question about a stable environment. I mean, there has been made much talk about that we should have a stable environment for developing life. As I have already showed you, variety is much more conducive to life development than stability. But I mean, one could take a typical example of a life form, the Scandinavians, for instance. In this scene, this idea about stability, they would go south in the winter to avoid getting too cold, and they would go north in the summer to avoid getting too hot. But what do? They go up in the mountains in the winter, and they go down to the Mediterranean in the summer, in order to enlarge the temperature difference. From which we can conclude that this requirement of stable environment is perhaps not all that good, or maybe the Scandinavians is not alike. So there has been this idea that dark moon is needed to keep the spin axis of the Earth stable, or else it will start tumbling around. Every 100 million years or so it will turn over. Now, if we had a tumbling Earth, I mean, the animals could probably manage to move 40,000 kilometers in 100 million years. And I think even plant life could, especially if the conditions of life selected plant life that were able to move its borders very quickly as conditions changed. So I'm not sure that there's astrobiologically any reason to have a large moon. It's nice to look at, but I'm not sure that's so important. Then the question about Jupiter. And the idea is Jupiter should remove the comets. And somebody should tell me how Jupiter should remove the comets. Comets come from all inclinations. And something coming from the top and going down through the solar system is not seeing Jupiter at all. It's not perturbed at all. And anyway, the low inclination comets that are perturbed, they will just get shorter orbits, so they will pass through here many more times very quickly. Probably as many times as it would have done if we had the long orbit. So I don't see how that reduces the risk of a cometary encounter.
Jupiter brings us water.
Then Princess Water, yes, but too much deuterium. But the point is, of course, that Jupiter is only affecting the Kuiper belt. Or rather, the comets, the short period comets that comes from the Kuiper belt. They are perturbed by Jupiter and put into short period orbits. Whereas the real long period comets that comes out from the Oort cloud is very little perturbed by Jupiter. So we could do it without Jupiter, but we need Jupiter in the picture to get the water to the Earth in the first place. So we need water, and water we have. Tectonics we will have at some time. I don't know when it started. I must admit that. But any planet sufficiently large should be able to have tectonics, especially when it has water. And even tectonics might not be all that needed. I mean, if we are going to find life on Europa, then it will be without tectonics. So one could imagine, for instance, now when we hear we can produce planets in binary systems, there would be a lot of tidal heating. That could probably provide enough energy source for life, even without tectonics. We still need water. It seems also, as far as I can see, that the idea that the walls of the cells are consistent of water attracted and water repellent molecules is a sure indicator that life started in a water condition. But we have bacteria that lives in the ground without water whatsoever, directly converting the rock.
And we always looking for at least the same film amount of things.
They can't produce that themselves? Okay, but that's interesting because it's just as interesting as that the bacteria and Surveyor was not there. So, but it's just to what can we then learn from this? Well, from my sort of running around talk, probably not much, but when we start thinking about how are we going to look for life in other circumstances, I'm not sure that we are choosing the optimum strategy if we are going to look for Earth-like planets. For the reasons I have sort of tried to sketch here. But I think we are in the same position as the drunken man late at night looking for his door key. And a passerby comes and wants to help him, and they are looking under a street lamp and they can't find the key. And in the end the passerby asks the drunkard, where did he lose his key? He lost it over there. But why are you looking here? Oh, the light is much better here. So maybe our best strategy so far is to look for something that looks like ourselves, because that's the only thing we know, probably for a long time. Thank you.
Thank you very much, and also for keeping your time. And I have interrupted some of the discussions during your talk, and maybe you can try to to put the picture of the early Earth where you have all
Yes.
these impacts, the heavy bombardment, the timeline of the reduction of the heavy bombardment
Yeah.
time.
I can probably find it
Because
better.
this is one of the, I think,
better one.
the reconstruction of the processes of the early Earth, where you have said many question marks, and yeah, that was it, one of those, yeah. And I think there are still more question marks which you have taken for given. But I think, Hildy, I interrupted you when you had a question.
opinion.
No, we can talk to the term after that. But there was first the reconstruction of the early and understanding the processes of the early Earth. So when the water came, and you had a question there.
Well, yes, sorry for putting it in the middle there, but I was just raising the question of when the tectonics came, because that probably was needed for the beginning of life, so that would help for the timing of the beginning of life, maybe.
At
Tectonics were not just
least for the deep,
systems of crust, but for the... Well, you might.
at least for the deep rinsing, you need tectonics.
Yes, they
Right.
And when did they happen here, in your time scale? When did you have continents or plate tectonics?
I said I don't know.
You don't know.
I know.
Maybe
But
nobody-
there might be a geophysicist that knows, but I'm not me.
No, but you don't need tectonics.
But
No.
Hotspot volcano is not tectonics, it's just a weak crust.
If life was starting to have the moments,
But then you get that just from hotspot volcanism, and that you don't need tectonics for that, you
Yeah.
just need a thin crust. So I mean, you need a thin crust to sort of isolate the water from the...
But where do you have the same cost? You have it where the plates are moving.
Yeah, but I mean,
You could have-
it takes a little while to do it.
You could have variation
So
in the
the
thickness
crust
of the
will have
core.
been thinner than 20 kilometers in the beginning. It must have.
but that was quite early probably, that was decided for
But isn't in Europa there's supposed to be a hydrothermal vent there?
Yes,
It's,
would be
uh,
nice, but it doesn't have, it's not due to tectonics.
Exactly. And does it have the thin crust? Also not, maybe, right? So we don't
There
really
was how many kilometers of water?
100. Yeah. Right.
Yeah.
According to the latest.
I mean, I have some more concern with these. I mean, this is at the moment, I think we have to put question marks for that,
Yeah.
because there are some groups which suggest that the isotopic evidence could also be later contamination by other microorganisms. You cannot, if you do a wide analysis and not a local analysis of the little fossil, then it could also be, especially the Ishua rocks, that they have a lot of metamorphosis, that the isotopes you determine are from fossils, but not from fossils that are 3.8 billion years old. So this is something, I mean, I like the history so much because we can say this is at the time when Mars was already, had a good chance also to have life, because they had water at that time.
Yeah.
And also the earliest fossil evidence of life is at the moment under
Oh
discussion.
yes. Oh yes.
The shops, cyanobacteria are very much under discussion.
Yeah.
But there are other people like Francis Wester who thinks that bacteria from hot springs fossils are about 3 billion years old or so.
Okay, so everybody can agree on 3 billion years. So that's that's an establishment.
Yeah. And there are only very rare sediments, I think 3 or 4 in Australia and in South Africa. And you don't have older sedimentary rocks than 3 point. So I mean, you don't know if
We don't know on the
You
other.
don't- you
we
don't
know on the
know
other
what
side.
happened
No.
here.
No.
Yeah. So it's not necessary that it had long time, 400 million years, maybe it was short. Yeah, please.
Yeah, I have a question in connection with this, that's putting it out to the audience. In connection with the ideas of life originated deep down in the Atlantic due to the fact that there was very heavy bombardment in the first 5, 6, 700 million years. Is anybody aware of a project that aims to retrieve possible fossil remains of that life through drilling? into the old sort of continental seeds that have not been recycled through electronics.
Actually, that was what the Cillian thing was all about.
Okay.
But that was based on Ruth's idea about not the formation from the street, but the earlier formation of the natural gas. What were these things? Well, they didn't find much.
On this curve, where approximately do you expect that the moon was formed? Yes, right. So what is the, isn't there a possibility that life may have already existed and then be destroyed prior to the cataclysmic bombardment? It's a possibility, right?
That's what I'm saying. Everything is possible.
And the question, of course, is...
Let me put it like this. The point I'm trying to make is that at the moment we are treating the development of life in a fragmented manner. We find some interesting evidence and then we discuss how life is developing around here, making assumptions that we don't check backwards and forwards. And I think that one of the very important things to get out of this exercise of astrobiology is to get our act together. Our act together. To come up with an offering called a unified picture, or maybe 10 unified pictures on how life developed that we can sort of put the evidence we find into.
I would like to ask, being completely outside, so this is the first kind of conference I'm at. So turning upside down more or less this argument and do it in such a way that first assume that life is very fast to create, and then the more complex life is, the easier it is to destroy it. So it requires very small changes. And then what we actually should look at here is what are the mechanisms of killing this more advanced life, so that we essentially have an incomplete way of seeing where we have life, because we have only very few sedimentary observations, so to say. So that is one complication. But the other one is that it may be that life is created, destroyed, and then when it really takes off at about 500 million years old, that means that we have got under some kind of disturbance threshold in this bombardment, and that gives just enough space for this to climb over some kind of evolutional exponential growth.
Yeah, but that there is some interesting. Again, that is something I'm not followed up. But I have seen some notice that the people trying to do these RNA studies to go back to the last common ancestor seems to end up with a commune instead of an individual, which perhaps could point to that if you are destroying life again and again, you're not destroying it completely. You are leaving pockets around that are able to intermix and thereby have slightly different RNAs to contribute to the pool. So, I'm not defending any viewpoint here. I'm just raising questions.
There's a few points what I would like to just throw in here. And one thing is that to me these time scales look a little bit of absurd in the sense that thinking about microbial evolution, at least as it goes now, it is extremely fast. Like biology's RNA genomes basically, for instance, replicate in a matter of seconds or even maybe less than a second. So 100 million years for a molecular evolution or microbial evolution is a huge time span, and it can really kind of establish and change within a year, not to talk of 100 or 100 million years.
Well, you can just ask how quickly a bacterium can become immune to the latest medicine.
Yeah, and if we would have unlimited resources, so E. coli would fill the earth in a few days.
But that is horizontal gene transfer, that goes through plastics.
Oh, yes.
Yeah.
But and that's I think is the point I've seen made a lot of times, that building up the basic engine of replicating and energy transfer and so on is such a complicated thing.
Yeah, and of course it was early on it was very slow replication compared to present, but still it may have become quite fast also early. But something what is probably very dominating factor here is the resources and ecosystems kind of internal interactions. And you had actually excellent points here pointing out the different things which have affected the development of Earth. But just thinking how very adaptive life is. So life probably would have adapted to once it started, so it would have adapted to any conditions what were there.
I mean, natural selection works.
Yes, and the conditions have determined of how the biosphere has developed complexity. And actually, it was an ecologist who kind of pointed out. I was wondering about where the complexity has come from, and some ecologists said actually, this comes to ecology, which is very complicated also, is that it is the complexity of ecosystems that drives species to become more complex because they have to adapt to more complex needs. So it also this interaction of different species with each other kind of drives the system. So life always adapts, and when the conditions get complicated, then life becomes sustainable.
That is also one of the reasons why the eukaryotes were so successful, because if you see that you by cannibalism you can utilize about for the eukaryotes about 10% of the energy, whereas it's 40% for the eukaryotes. Then you can have many more generations or levels, species, before the energy in the feed chain figures out.
And I have a feeling, now this may be wrong, but I have a feeling that the prokaryotes increased and kind of dominated the Earth as long as there was space to just kind of increase at that level. But when the niche was completely filled, then more complex organisms developed on top of that.
But they are not extinguished. That's important. So the microorganisms of bacteria would never extinguish.
Yes,
But the whole,
but then the higher ones develop into the next niche.
yeah.
They are not to be like, they are actually living on the prokaryotes to some extent, but they are not living in the same niche.
But could that then be an explanation of all the extremo fields, that there was a period where this kind of species were threatened and therefore had to move into very unpleasant surroundings? Or why do we develop extremophils if we have more natural surroundings available?
Right, okay, but there are the three niches, and then these organisms just gradually adapt. They love it there.
Yeah.
Can I just
I
ask?
think we move now to the general discussion. So I first would like to thank. I would like to invite you to stay here because the discussion goes on so nicely, stimulated by your talk.
Yeah, I had a question in order to understand the issue. Am I correct that first of all the eukaryotes are already eating other living beings? Is that correct? But the prokaryotes are not.
Oh yes.
They also?
Hey, eat one another.
They're both of them
We
then.
have both groups. We have autotrophic.
Yeah.
They build their biomass from anorganic substances, and you have heterotrophic, and they
Yes.
use organic substances to produce the others or dead cells and so on. So
Right.
we have both.
So the autotrophic ones are which one on the tree? Here and
In
then,
bacteria, you have some, I don't know.
Photosynthetic organisms with a
yeah.
Photosynthetic and
photosynthetic of plants, and then also chemoorganisms.
Yeah. And you have bacteria who live
The point I made was that by having a nucleus, you could make the cell so much bigger that the small cells couldn't eat it, whereas the big cell could eat the small cells. So
even engulf the small
Yeah.
cells and let them work, like the mitochondria plus
chloroplast, yeah.
I have one question which came in my mind when does this group somehow have a feeling did life start once on Earth? Or when you have these catastrophic events, do you really think that life could start several times on Earth? And why is then everything based on the same organic chemistry and the same biomolecule? So does somebody have an idea? Do you think more life started once? Or did we have several times? I mean, that would mean that life always starts in the same way. Is there some idea?
I think life started like this.
But you never went down to zero.
Right.
So there's, and why was it then one point that life started? Why does it happen today again?
I have very big difficulties in even thinking that it will be only once.
Yeah.
I think that there is only, we have 100 elements basically. And there's only a finite number of ways we can build this. We have 100 Lego blocks and we have to construct everything from that. So there is certain, I think, structures simply that are available and possible only. And somehow I would be tempted to say that we have these shmups, essentially as a starting point, and they construct certain structures. So there is probably some kind of maybe simple box or whatever. I don't know really what kind of structural polymeric things that we need to create. And these are certainly some kind of natural inorganic stuff which then could serve as something. So you drop it into the water and then you have a fishing net essentially. Something like
There's
that.
something else.
Yeah, are you sure? Because here we somehow also have some kind of in this argumentation we come back all the way to some kind of hand-waving Munchausen-like technique of arguing now. And this I find quite dangerous in a way. Because exactly with the same logic I can say that yes, it starts over and over all the time. It's exactly equally strong argument. With the difference that chemistry we know something about, physics we know something about, and we have some observations surrounding it.
So you would think it's
Yeah, I think that giving the right conditions, life will always start, and it will start everywhere, essentially.
even if there's already life.
Yeah, it will be slower, for somebody will eat it.
But now the other evidence is that life here on Earth is all of one and same kind, and it is of very limited properties now, chemical properties.
Yeah.
Now starting from the very starting materials, which would be the cyanides and aldehydes and methane and water and hydrogen, you will make amino acids and you make sugars, you make nucleic bases, and life is made of these, but it's made only of 20 amino acids, although you can make hundreds of them. But all life is using only the same 20 amino acids. And all life is using homophenolic left-handed nucleotides, although you could just as well select other phenolic. And
Only the 20 amino acids,
yes.
where we have individualized.
Yeah, so basically we are very well limited all life here to the same chemical composition. Our cells are all functioning by the same machinery, tRNAs and ribosomes. Yeah, I feel very much related to E. coli.
Very true, you are almost similar.
Yes, chemically they're just the same.
Yeah, exactly. exactly, but
So
then,
you cannot make the same thing over and over again and come up to the same method.
are you sure? This is just an argument without basis. We have an observation, but once life starts, then there's a competitive process. And this competitive process will, for instance, chirality probably modify into a certain direction. So there's a competition between two.
Yes, but it's not modified the existing genes, which are evolutionarily very conserved, and they kind of select the chirality. But that means that those genes come from the beginning, and they come to all of us.
Yes, or the others are tough.
But there's also the point that the DNA string seems to be extremely similar for all the various individuals we have
More or less the
investigated.
same. The principle is the same.
The principle is the same, but if life has started
Yeah.
several times, then you would expect to find DNA where several blocks were not in the same place. Their functionality would not be impaired, but why do they have to come in the same sequence if there are no relation? I mean, there might be a reason. I mean, there might be a good reason that it always has to be like this, no matter how many times life started. But my initial idea would be that if life started over and over, there would be some difference.
Now you're making a very strong implicit assumption. You make the assumption now that life would start in many different ways. But what if nature has arranged in such a way that it can start only in one given way, that it automatically goes into this one? Because this is an argument exactly again that you are putting in explicit other different arguments in.
But one argument is that evolution is repeated.
May I just answer this one? I was not putting that argument in. I think you misunderstand what I'm saying. I'm saying what we are finding is that all DNA are alike.
Yes.
And if it could start in different ways, until we come up with a reasonable argument that all of the sequences should be placed in the same place in order to obtain life. We can mix them up in so many ways and probably still not impair the functionality. And there are all these empty chains also sitting around. Why should the empty chains sit in the same place every time you start life? Because as far as we can see, they have no function. I mean, that might be our ignorance, but as far as we have seen so far, they have no function. And therefore, I cannot see any compelling reason why we should have junk sitting in the same place in the DNA string unless we are related.
Okay.
Are there some more? Yeah, please. Yeah.
I was thinking about maybe the life it has actually component out the earlier life that was different. And that would be an explanation for the CO, there is the DNA.
It has extinct the other one.
Actually, that is one of the arguments why the deeply rooted branches are all thermophilic microorganisms. One idea is life started in a hot pond somewhere, in the heart of southern America or somewhere, in a hot environment. The other is that by these catastrophic events here, by the bombardment, the earth was heated up so that nearly all water disappeared. You say not all water, but it was quite hot, became quite hot. So only the very hot-living thermophilic organisms survived, and they gave them the starting point for the rest of the life. So maybe that's one of the ideas. Maybe life at the beginning was much more versatile, but only one kind survived. So these are different hypotheses. Yeah, please.
Can different like for the paper, like the musical rivers and things like that, can start using the same codes and grow together. I mean, if we have two lights and one use 10 animal acids and or 10 amino acids, and they go together and start using 20 amino acids. Or something like that. Just trying to point out that can they evolve so that they look like same.
Nice idea.
When probably this has happened to some extent, and the reason is the lateral gene transfer, that we all organisms have exchanged genes back and forth, and so we have shared the genetic ones.
And maybe different constraints like begin and then because
The best combinations finally evolved.
But in the RNA world, is all 20 amino acids needed?
I don't know, good probably started to use the 20, or code for the 20 amino.
We have one comment.
Yeah, but it seems that one of the really controversial things about is also protein information. I mean, there's EBC neutral, which shows sort of how DNA is from tRNA actually, I mean, the alphabet, how these three codons code to an amino acid that sort of life forms that will evolve in parallel and choose exactly the same mapping there. It's highly unlikely. And I mean, even if they co-evolve, then sort of transfer a gene, and then this other organism has a completely different mapping, the genes will be
but
expressed.
can they evolve if you have two different kinds of
If they use, I mean, then at some point they need to start using the same tRNA, and
if there is two,
then the meaning of all the genes will completely change, right?
yes,
They won't map to the
there's
same
different
protein,
ones.
so
If we have two kind of like one element is that we can, I'm not sure why can since it's both sides can be those any more weak. If we have two systems, then only one is necessary. So if they come together, I don't know how it can give its own, like what liquid. Can really metabolite and everything like that. Well,
will not use its genes.
Is that something one could try to solve in a computer model system? Maybe
The other thing I would also ask, because of my ignorance, is simply that these so-called rubbish parts or unused parts in the DNA sequence, have they possibly been used at some earlier stage to synthesize something else, some other parts? So have they been an essential part in the evolution, essentially, which is not seen anymore in the life forms we have?
Well, probably there have been some sort of functional elements at some point. For instance, retroviruses, or say already getting out of elements which have been recombining in different ways and then making larger and larger genomes. And then if you don't need all the functions, you may lose the, I think that it is composed of genes in the first place, some kind of functional genes. But if you don't need the gene anymore, then you just may lose its starting elements or regulatory elements which kind of make it function. And then with time the whole code kind of erodes away. So a lot of these kind of non-coding areas probably have at some point been coding something, and then they have just kind of lost the code. There is a lot, for instance, of these duplicated sequences, so that it has been a sequence for something first and then it has been duplicated multiple times, and it has been kind of creating take copies of itself. Unfunctional copies of itself. Or it has been originally viruses which have then been integrated into the genome and lost their function.
That is what I mean by this evolution. Then again, that
As a sense,
yeah, so in principle it could be that it's what we see essentially some kind of attractor of a very strange kind, that it's a nonlinear system and then everything is attracted into a certain direction. That is the kind of thing.
I think we can not solve the problem completely. Maybe if we really search for life on another planet like Mars, and we find something which is identical to the life on Earth, or different,
Has
a
it
little bit different,
has it been originated on Mars or has it migrated?
has been transported to Mars, but at least this would give us a very interesting new perspectives. There was one point.
I would like to return to this previous theme and specifically this picture. I think that the early evolution of Earth chemistry was not affected by this, not negatively affected by bombardment, but rather the opposite. In fact, in Reykjavik there was a paper on this topic, how the bombardment might have promoted the formation of molecules vital for the conception of life later, and even such a reaction.
Maybe you speak a little bit louder in order to be understood.
Okay, yes. So the early chemistry, as does inorganic chemistry, occurred today in the pentasecond time scale. So such catastrophes in a so early stage of evolution of chemical life, abiotic life, does not have no effect, no negative effect, but rather the opposite, because it creates different conditions where new kinds of reactions can occur and proliferate, begin to proliferate. So I think you should consider other factors, the level of evolution, the complexity measure, in fact, not only time scale, because that is very rough criterion, insufficient for the description of the early conditions, and not only the early conditions, but also the most advanced forms of life. I think if you would turn this picture upside down, it would give you a fine image of the rate of the state of evolution of the complexity. The end here, which is low now, would be up, but the rate of the evolution, this is rather the rate of evolution, because it is very low. It becomes lower when the systems become more complex, except for when new kind of mechanisms arise, such as the DNA. That was, of course, given all
There was one question, could you
order.
define complexity?
And one more mechanism which seems to be very important even today, sexuality.
Yeah. There was one question, can you define what's complexity? Very short.
Complexity.
Brief.
Well, there's a mathematical theory of complexity which is itself very complex, because you can have linear complexity, you can have planar complexity, and spatial complexity, and temporal complexity, and this involves all of these. For instance, the DNA is a linear complex dimension, and then membranes are planar, topological complexity, and all these which you have there inside this organelles, very complex topologically, and so on. Functional complexity, which is the computer, which is the universal complexity, which you can have in any form, but there it is in the very simple form because it is binary complexity, but it is equivalent to any form of complexity. Let us say the human brain, which is a network complexity, also discrete topological complexity. So complexity is a complexity.
But if you like this curve upside down, does that mean you consider unicellular organisms to be about as complex as multicellular organisms?
Of course. As a microbiologist. Look what happens all in one
Everybody
cell.
loves his atom with a crooked leg.
What happens in one cell? The whole complex mechanism of building up biomass is going on in one cell.
An important aspect of complexity is diversity. So it is not only one system complex, but having different systems.
Okay, yeah. I mean, don't want to spend too much on this topic, but
Yeah, I just caught on a term here. We talked about abiotic life.
Abiotic life, yes, very good, because abiotic is a traditional concept which does not fit into the theory of universal life. Because you have also inorganic life, as I mentioned, in chemistry, explosion chemistry is a scientific example. Also fire, normal, simple fire is an example of inorganic life. Extra life, not endless, of course. So we must have scientific definition which covers all forms of life, from nuclear to inorganic and so on.
Okay, one more.
I wanted to move on to something else. One of the most passionate discussions at the Iceland meeting came during a presentation of the terrestrial planet finder mission, which is a joint NASA-ESA mission, which is aiming at finding Earth planets, period. Only looking for planets like Earth. They're not looking for any other options. And the passionate discussion came from people with the point of view of IP saying it only makes sense to go looking for Earth-like planets because it's the only place we know it works, so let's just take that as the first option. And then people who I'm more in favor of saying, why be so narrow-minded? Why only look at planets like Earth? Why not look at whatever, look at not only solar-type stars, but stars with a shorter lifespan, but more energy, who will therefore have a different habitable zone. The whole thing about the habitable zone is already a bit questionable because, you can define it in many ways. So just wondering if maybe we should take up, since it was a very sort of heated discussion in Iceland, and it was unfortunately, it was cut off very abruptly because of not enough time.
Yeah, they actually talked about looking where we should not. So
Probably I have to cut off this discussion again. Because we have tomorrow, I think, a special session on, on extrasolar planets. Isn't there something like that? At least binary,
Areas and orbits.
yeah. So, because I was asked to close in 5 minutes.
Okay.
And so I think it's better when we have the talks and then we can continue discussion. But I still want to have a discussion about, at least some explanatory work on the deuterium-hydrogen ratio, and what is the reason that in different areas in the solar system, the deuterium-hydrogen ratio is different, and it wants to give us some talk.
No, it's basically, as far as I know, it's a temperature gradient. The colder the situation where the cometary nuclei are forming, the more deuterium.
The deuterium is volatile, so it's not very easy to incorporate into minerals.
Hydrogen
Hydrogen is also volatile,
Yeah.
which is also why you don't find very high many hydrogen bonded in the terrestrial gas, so I don't want hydrogen. So it is a temperature thing. I mean, it's not so easy to incorporate into a mineral.
I know that biology
You needed it
has an
ice.
influence on isotopic ratio, for instance, in carbon-13 deficiency, and there's also, I think, on sulfur and nitrogen that is influenced by microbes, but not in the global deuterium-hydrogen ratio. That's more temporal. That's what I have learned.
No, to incorporate the deuterium, you need it in the water molecule, which means you need to be out where the water molecule does not get destroyed. That's the only way, so you can incorporate it into ice. So you will only find it on the other side of the snow line, which is around the asteroid belt. You will not find it in the planet system. And the 3 comets which have been observed, so there's only 3 data points, right? So it could be that we had the 3 oddballs, and maybe it's not just nothing, but it could also be that they're somehow universal. They're all short period comets, so they might not be representative of the old cloud. But however, they do have a D/H, which basically, when you are an astronomer, at least fits what you see in the interstellar medium. I mean, so they do have sort of the ratio we would expect from sort of an interstellar cloud. And that's the problem.
So that solves that question.
But isn't one saying the water on Earth comes from comets which are nearby?
Not all.
Or are you now?
They have to be very nearby.
Neutralized.
They have to be, no, I mean, the latest is they come from the asteroid belt. You can call it
Yeah,
asteroid,
yeah,
or
yeah.
comet, so, I mean, where's the
asteroid belt,
between an
yeah.
asteroid or the comets?
But that is-
Whatever small object you have around the asteroid belt.
Right. But in the asteroid belt you have already a smaller D/H.
Yes.
And that D/H is the same as on Earth.
Out to Jupiter.
Yeah,
Right. Okay.
because the asteroid belt is on the limit of where you, that's why it's called the snow line,
Sure,
where you
yeah.
can start forming the ices and have the deuterium incorporated. Then of course, the further you are from the star, the bigger your chance.
So the deuterium has to be incorporated in the water in order to be stable. Otherwise it would go.
Yeah, else you don't get it into
Yeah.
the minerals. You can only,
Uh-huh.
you need it,
Yeah.
you can only get it into ice.
Yeah.
And you can only get it into ice by having it in a water molecule. I mean, it's not, well, you don't really need it in any minerals, right? It's not like, it's not, your
And that's why it's enriched on the outside, although it's colder.
Yeah, that's why it needs to be cold,
Yeah.
because you need to have the unbroken water molecules which then condense into ice. Then you can have the ice melted into with the rocks and have, you know.
In which other place are these synthesized in? Were they always synthesized in the Big Bang?
No, only the helium and hydrogen is from the Big Bang,
Yes,
and
but-
the helium and everything else is from
Yes,
the
but
sun.
the total thermometric and hydrogen was from there, but in what ratio were they made? Were they made in
10 to the minus 4.
Yeah.
more hydrogen?
That's the canonical number.
Okay, so there's minimum amount of deuterium.
Oh yes, deuterium is a trace element in
Yeah,
this.
yeah, it's basically, it doesn't exist. I mean, it's not there, really.
So you can still find it out there.
Yes.
In other
Yeah.
things, so.
And the reason there's only 3 data points for comets is it's not very easy to measure because it's so,
Well,
so abundance that it's very hard to get it.
Or one should rather say that we have started since we have started measuring isotopic abundances in comets, there have only been 3 good comets to measure.
It's
Halley, A. Bob, and
you are, no, I don't think you are the time
Cooley. No, it wasn't.
But in Stardust you don't do that?
No, we don't have enough data to be able to do that. The massive solution is not good enough.
Stardust
But it's-
is
And then there's also one question, what
I know.
the
So
water.
they evaporated the water. Okay, so I think we had quite nice discussion and from early Earth to the comets again. And now I hand over to Axel. Maybe you want to say something about dinner and
Yeah, no, thank you first of all for sharing the session. And I think we are otherwise all right. I mean, are there any questions that you have to ask regarding the organization of the meeting? No. Right. So then There will be the dinner, I think that is at 8 o'clock, right? And what else? And then what is
Where's
on
the
after that?
dinner, where the reception is?
At the cafeteria, building 1 on the map. If you.
Direct to the restaurant business.
Yes,
Okay, yeah. And what about breakfast tomorrow? When does it start and when does it end?
Now, I don't know those times, we need to ask the cafeteria staff, but I think it is served for quite a long time, probably starting at 7 and hopefully 10, this is my guess.
We start at 9, but anyway.
Yeah. And then there is the sauna behind that same building, and it is good for us for the evening, I don't know if it's.
Also this evening.
Yes, we have the sauna by the sea for tomorrow and Saturday.
Ah.
The local sauna for this evening. And we also need to ask the staff of whether it is already warm. You might want to go into the sauna even before dinner if it's already warm.
Is that true? I mean, you will have the sauna for the whole time? I thought, yeah?
Yeah, I thought we cannot ask about the times, because we also need to share the turns for males.
Yes. Right, yes.
So if you give me comments, I'll be back with the times for the sauna.
Yeah, okay.
Can you give me the telephone number from the place and also,
Yeah.
if you can find that?